Chapter 3, no, Part 3, Chapter 8, Taking Chances for Fun and Profit. With Chapter 8, we find ourselves moving into the heart of real statistics, and hopefully you will see that it is not that intense. For you students who have an affinity for statistics, this chapter will be just a teaser of things to come. What you will learn in Chapter 8: how probability relates to statistics, characteristics of the normal curve, i.e. bell-shaped, how to compute z-scores, and how to interpret z-scores, and how to interpret the area under the normal curve. Probability is the foundation of statistics, or perhaps the mother of invention for statistics. The normal curve, for which we will go over in this podcast, has its origins in observations made in the real world. Essentially, with enough observations of a measure in a normal population, the vast majority of observations would cluster around the mean. The further away from the mean one gets, the less likely the probability is that it happened by chance. Combined with the concept of the normal curve, this promotes predictability, a.k.a. the probability that a possible outcome will occur based on some known data, and by extension, the confidence that a probability or an outcome is true based on its own merits and did not happen because of chance. Statisticians have represented the normal distribution visually and graphically as a curved line. This line is perfectly symmetrical, meaning there are equal number of values on each side of the middle of the curved line, and the mean and the median and the mode, the main three measures of central tendency, are all equal. And finally, and perhaps less important, since it is an abstract concept, is the tails are asymptotic. We use visual representations because, well, let's look at the visual representations in the next slide. First, here is that abstract concept called asymptotic. But that simply means that as this tail curves down, it will start to curve out and away from the mean at an ever-increasing rate and will never actually meet the x-axis. When we read a bell curve, or really most any lined graph in statistics, we look at the area under the line. We can see that the area under the curve is symmetrical, that the left side looks like the right side. Those values below the mean are equally distributed as the values above the mean, and of course the mean, the median, and the mode are all identical and are so represented by the vertical line. Now, going back to the idea about research being about the ability to generalize, and that requires understanding of distributions of central tendency. In these examples about smart people, or the smartness of people, and the height of people, and they are two separate examples. So don't think that this example implies that the very, very tall are also the very, very smart. Further, it is important to remember that the hump in the middle of the bell curve is not caused by summing together all the heights of those who cluster around the mean, or summing together the smartness of all those who cluster around the mean, but it is accounted for by counting their number. Along the y-axis, that is the one that runs up and down, it is labeled few people to lots of people. For line graphs based on a single vector or variable, such as height, it is appropriate to graph them using the count of cases only. Let's look at an example. We have already learned about standard deviations, or at least how to calculate them in Excel. The standard deviation is one of those basic statistics tests that we calculate in order to understand our results more fully. So when we have calculated our descriptive statistics, and we have a mean and a standard deviation, we can look at any individual observation in that sample and tell where it lies in relation to the mean, and really to all the other values. However, the standard deviation is related to the size of the mean or the units of measure. And when we have samples drawn in different studies or from different populations or ones that have used different measures, we lose our ability to compare the two directly. The need to compare distributions led to the creation of the z-score. Let's take a look at what we're talking about. As indicated in the previous slide, almost 100% of the scores in a normal distribution will fall between -3 and +3 standard deviations away from the mean. In this example, based on a normal distribution with a mean of 100 and a standard deviation of 10, what we would be saying is that nearly 100% of the individual cases in that distribution would fall between a raw score of 70 on the left and 130 on the right. So here we have 70. To be exact, just 0.26% of the cases will fall either above or below that range, with 0.13% residing on the left tail and 0.13% residing on the right tail. This whole idea of tails will come up again later when we are discussing t-tests. Let's look at the numbers. The normal convention is to line chart from left to right. However, since a plotting of a line of the distribution of the normal curve has a mirror image of those values above the mean with those values below the mean, they could also read this chart from left to right, or right to left. You might have also noticed that the histogram assignment created something vaguely similar to a curved distribution, albeit by using bars. And those of you who select the option for a line of cumulative percentages will recognize the percentages that I have added here. $13% plus 2.1 1% equals 2.8%, plus, you get the idea, and so on around the curve. Knowing these cumulative percentages gets us at the first step of understanding our probabilities. But first, we have to understand what all this means. The most important thing to keep in mind is that the two standard deviations either side of the norm, -1 to +1, account for over 64% of the total distribution. Nearly 2/3 of a normal distribution will lie just one standard deviation away from the norm. Said another way, once we understand this idea that every standard deviation owns a certain percentage of the total distribution, and that those percentages are constant between samples, we start to get at how we can compare distributions based on observations that can be radically different. This isn't just comparing pounds to kilograms or studies that use inches versus centimeters, but the fact that each standard deviation has its unique topography, owns a certain piece of the curve, enables us to compare things like measures of weather severity when one study compares perhaps snowfall in inches and another temperature in Celsius. These slides are based on tables in Solkind. I'll skip them so we can save time for the z-score. Here's our formula for calculating the z-score. What are those symbols? Here's the legend for those symbols. Where x is the individual score or observation, and bar x is the mean of the distribution, and the lowercase s is the symbol for standard deviation. When reading this equation, or the previous equation, in common English, one would say z equals the value of an observation minus the mean of the sample from which it was drawn, divided by the standard deviation of the sample from which it was drawn. Straightforward enough. Z-scores can be positive or negative, and when you see a negative z-score, you will know that the value is less than the mean, and when it is a positive number, it is greater than the mean. If you happen to see a score that gets a z-value of 0, and it can happen, that means that it is equal to the mean of the distribution. Excel can easily calculate a z-score for you. If you have trouble understanding the sequence of calculations in Excel from reading the text, then take a look at my separate recording titled Computing the Z-Score Using Excel. By looking at the raw score, the mean of the sample it was drawn from, and the standard deviation of the sample was drawn from, we can calculate the z-score. And when we know the z-score, we know where an individual score lies in the distribution. So we know how much of a percentage of other observations are below it, above it, or between it and another observation. So by sticking with the example of a distribution with a mean of 100 and a standard deviation of 10, we can calculate the probability for each individual score. So when we have one standard deviation above the norm of the distribution that has a standard deviation of 10, i.e. 110, then we can easily tell by adding together all the values of the percentage under positive 1 standard deviation, which will give us 84%, well, 84.13%, but let's not quibble. Similarly, I know that 64.26% of observations lie between -1 and +1 standard deviations from the mean. Therefore, the probability of a value falling between 90 and 110 is 64.26. Simple? No? Okay, let's move on. Table B, point 1, which is found in the back of the text, will be available in almost any statistics book. It's too small here to read, so we'll just skip over this. Coming back into Excel, we can see how we can use that program to calculate the z-score without having the entire sample. This will allow you to calculate the probability when you only have the mean and the standard deviation along with the raw score. When your z-score doesn't happen to fall right on a whole number like 1 or -2, then you have to rely on the table to calculate the differences between the two scores. Doing so just requires you to go back to table B.1 and follow a simple 3-step process, which is actually just adding and subtracting. Actually, I should say table B.1, which is on page 373 of the 3rd edition. Let's get back to some pictures. Too many words. For most folks, it is easier to visualize what we are talking about here. We saw earlier 1 standard deviation is 34.13% above the mean. 2.5 standard deviation lies 49.38% above the mean. And we simply subtract one from the other, and the result is 15.25%, which is the difference between the two. Since we don't always have a statistics handbook lying around, well, I always do, you can probably simply use Excel. You can simply use Excel to calculate your probability for you. Hey, that is nice. Using the norm sdist function, which is a part of any distribution of a spreadsheet application, Excel or OpenOffice, Mac, Apple, Windows, or Linux, it's all the same. Although you might sometimes see it also called as normdist in some of those other spreadsheets. Here is the same problem we worked through previously. We have 2.5 standard deviations above the norm and 1 standard deviation above the norm. We calculate that probability using Excel, and then we simply subtract one from the other. The result is the same. Excel's process is a little different in that it calculates the probability from 0 rather than from the mean. By now you've read enough research articles that I'm sure you've run across the following symbol. P is less than 0.05, which, or perhaps you've read in a text something about the results being at a probability level above 95%. This all goes back to that normal curve and the ability to calculate where individual scores fall on the normal curve. 0.05 is just a convention agreed upon by social scientists. So when you see an individual, so whenever an individual sees a score that is 1.65 or greater, regardless of the sign, you know that you are inside of that 0.05 range. Z-score, I should say. How do I know this? The text says so. And I've calculated in Excel in this example. Plus 1.65 standard deviation is 0.9505 probability. And minus 1.65 standard deviations is 0.0049. 0.049. And remember, Z-scores are typically reserved for populations or samples drawn from populations. Well, that's enough for now. Too much, some would say.